before you go. Yes, they are graded.
It is graded.
Yes, they are listed on Blackboard. So.
I checked it this morning.
No, you checked the wrong one. Did you try blackboard.sccans.edu?
I just checked it.
I put on EDV. So that's EDV. I'm sorry. I guess I should have told you that's the backup site. Alright, so a couple things left to do. One thing left to do out of 2.4, and then we'll move into 2.5. So last time we were talking about measuring the spread. We had that standard deviation tool, and we also spoke a little bit about how when we had bell-shaped distributions, the standard deviation allowed us to look at various properties of how much data was in varying ranges. One last thing to talk about with the bell-shaped distributions and these standard deviation aspects. One thing that we saw with that empirical rule, if you remember, there were 3 parts to it. One standard deviation from mean. We had how much data? Right. When we went 2 standard deviations out, how much data? 95 there. And then 3 standard deviations, we had 98 or 99.7%. And what we can actually do with this is there's actually one little bit of extra information that we can sort of squeeze out of this empirical rule. And it basically says the following. If you were more than 3 standard deviations away from the mean, it's highly unlikely that that's going to happen based on this sort of rule that we have here, right? Because 3 standard deviations, 99.7% or almost all of our data is within 3 standard deviations. So if you're more than 3 standard deviations from the mean, that's a very strange occurrence for these bell-shaped distributions, okay? Anytime we have a bell-shaped distribution and we have a data value which is more than 3 standard deviations from the mean, that particular data value is often given the term potential outlier. Okay? Outliers are these data values which can sort of be thought of as, do I really want to think of this as part of my data? They're those values that sort of are so far different from the rest of the data that you have to be a little bit skeptical about whether or not they are valid data points. So data values more than 3 standard deviations from the mean are uncommon for bell-shaped distributions. And one thing you can do to figure out you can do to sort of identify whether or not a value is more than 3 standard deviations away from the mean is you use what's called the z-score. And we will see z-scores used a lot in the latter part of the class. But a z-score is basically just measuring how far a given data point is from the mean. Okay? The z-score, the formula for z-scores look like x minus x bar divided by s, where here x is our data value. X bar obviously is our mean, and our s is our standard deviation. Okay. So in statistical language, this kind of thing, using these z-scores, is a useful tool to identify sort of uncommon or strange data values when we have nice bell-shaped distributions. Okay? As an example, just calculate one real quick. For the football one that we had an x bar. X bar was 39. Our s was 13.2. We had a data value of 85. There was one data value, one team in the football conference that had 85 touchdowns. Now, how many standard deviations away from the mean is that 85? Well, to calculate that, that's what this z-score is doing. It's telling us how many standard deviations from the mean this particular value would be. And in calculating that, this is the notation that I will use whenever I'm calculating a z-score. Z-score, down here, the little subscript represents the data value for that z-score. And in this case, I'm just going to plug these values into that formula over there and figure out how many standard deviations this 85 is away from our mean. All right? So we plug everything in. We do the subtraction. Let's see, that gives us a 46 over 13.2. Calculate that. What was it, 3.4?
49, yeah.
Okay, 3.49. All right. So we see here, this particular value, 85 touchdowns, is more than 3 standard deviations away from our mean. Okay? I have to go almost 3.5 standard deviations away from the mean to get this 85 to be within my range of values. Since it's so far, or since it's beyond the 3, we should take a little bit of time and really ask, is this a realistic value? Now, we know there was a team that scored 85 touchdowns, so yeah, it's realistic. But it's very uncommon based on the rest of the data that we collected. This score of 85 touchdowns is very uncommon, and it's not something we would typically see in a normal season if we were to go through and look at the number of touchdowns each season. Okay? All right, so potential outliers. This is how we go through and look for what are called potential outliers. Is we calculate this z-score. It's bigger than 3. Good chance that that's a strange observation. Okay. All right. Questions on this? We will see this formula a lot. So understand what it is, understand how to use it, and what it's measuring. All right. Then this gives us time to move into 2.5. 2.5, we're going to start talking a little bit about how to measure position of data. Measuring the position of our data is another way that we can analyze how our data looks. In measuring position, there are a few terms that come up frequently. The most common measures of position are what are called percentiles. Now, what is a percentile and how is it used in statistical terms? Well, all of you, I'm sure, have at some point in time in your life taken a standardized test, ACT, PSAT, SAT, one of those. And when you got your score back, what it gave you is it gave you something called a relative percentile. For example, on the ACT, your score of 34 is listed as the 95th percentile. All right, what does that mean? What does it mean to say that the score of 95 puts you in the 95th percentile? Well, if you think about what the overall aspect of the ACT is. The ACT is a score out of 36 points. You've got 34, 95th percentile. In some ways, you should be thinking that that 95, this percentile, should put you near the end of the distribution of scores. And in fact, if we look at a distribution of ACT scores, approximately bell-shaped, that's irrelevant here. But the 95th percentile, this is where the 95th percentile would be. Okay? That little vertical line there represents our 95th percentile. Now, in terms of looking at this picture, how could you interpret that 95th percentile? How should you interpret your 95th percentile score?
5% of the people did better than me.
Go ahead, Rodney.
There's only 5% of the people who took the test that scored better than me.
Right, so in one way, you can look at this 95th percentile as saying that there's only 5% of people that scored above your score. And that is one way that we interpret it. The reason it's called the 95th percentile is because 95% of the people scored less or below your score. Okay? That's why it's given the name the 95th percentile. Is that you're talking about what percent of people you scored better than. Okay? So the percentiles are a way of sort of measuring your position along this distribution. All right? If I was to talk about the 5th percentile, well, the 5th percentile would, again, sort of be down here somewhere. Our 5th percentile, again, interpreting it in terms of this idea that we just talked about, the 5th percentile says that 5% of people scored worse than you. And I realize that sounds very negative, I'm sorry. You scored better than 5% of the other people. Okay? That's what these percentiles are doing. They're just measuring your position with the rest of the data that is collected. Now, for our purposes, these percentiles are nice, but there are a couple of special percentiles that we want to really focus on. And those percentiles are what are called quartiles. The quartiles, as the name sort of suggests, are the values that sort of split our data into 4 different groups. Okay? The quartiles are listed as Q1, first quartile, Q2, second quartile, Q3, the third quartile. All right, now the term quartile should indicate to you, much like a quarter, you're talking about 25% somewhere. Okay? So when I talk about these quartiles, if I look at sort of a distribution here, the first quartile should do what? What's the first quartile measuring?
The first 25%.
It's measuring the 25th percentile. All right. If I look at my graph here, and again, I'm not trying to be 100% perfect with this, so bear with me. The 25th percentile, right about there, also Q1, 25% of my data is below this value. Okay? All right, well, what about Q2? Q2 marks what? It marks the midway. Q2 represents the 50th percentile. Right. This value is often given what other name? 50th percentile marks what?
Half.
It marks half. What data value or what other statistical term have we seen for that? The median is the other name given. The more popular name given for the second quartile. Okay? So the second quartile, 50%. How much is in between Q1 and Q2? Better be 25%. Right, and then finally we have the third quartile. The third quartile measures the what? Also called the 75th percentile. That's our Q3. And 2 ways of interpreting that one. There's 75% of my data below, or there's 25% of my data above. Bless you. Bless you again. All right. So in looking at our quartiles, there's only 3 quartiles. There are only 3 of them. But what they do is they split our data into 4 groups, each with the same percent of data within those values. Bless you. How many times have we made this? Anyone else need to sneeze? Get out now. Let's go. No? All right, so these are the quartiles. Now, let's actually find some quartiles. Okay? Finding the quartiles is a very straightforward process. We've done something similar to it already. We need to do it again. So I'm going to put some data up here. These data values represent weights for varying people in this class. I won't say who, but here are the weights given. Find